One way to put it in the bag, you can screw up. If they do like workshop, right?
Yeah.
Then they are doing that.
I think it's a lecture first and then a workshop.
Oh, then just for the classes. We can turn off that one. No?
I think that's what they're trying to do.
I think it's fine.
So I guess we're probably going to start class now. Hi everyone. So anyways, I'm Oliver. I'm one of the instructors of Practical Lab.
And teacher, I'm also a teacher.
Yeah, and so why don't we just go over introductions again?
Yeah.
So I guess check this out.
Okay. I'm Isha. I'm Ria.
If it's school work,
I'm from Ghana School. I'm from Toronto. I'm Michelle. I'm Shady.
Okay. Thanks so much.
So, I'm a teacher. I'm from principal.
So, welcome back to class 3. Can everyone see the screen properly? Can everyone see the screen? Camera's one. Okay, so today we're going to be doing, today's class 3 and it's the introduction to neural networks. Okay. Yeah, welcome, we just started. So, actually, give it on to the, so yeah, okay, so, a brief overview of the lesson plan. We're going to go over some like homework survey and announcements, yes. And then we're going to be doing some review. We're going to be doing like the 3 major models that we covered so far. And then we'll have the rest of the time for neural networks. And then after the lecture, there'll be a briefing for military communication time. Yeah.
Where we will get to build our own networks, both a classification task and
So, I think Nandita's going to be sending around a homework survey, and it was different from the one before, and it kind of like keeps track of what homework you did, and so yeah, we'll be sending that out soon. And and then I was gonna just say like, if at any time if the homework is unclear or something, it's always going to be posted on the Practical AI syllabus, and also the office hours are there as well, and also and the other which days are the other classes. That's all posted on the syllabus. So the syllabus is amazing. Yes. Okay. So. Yeah, wait, so, alright. I'll try to speak a bit louder. Okay. That sounds good. Alright, so, I guess, oh yeah, wait, is the clicker not working? Alright, okay. I guess we're just going to move on to the review then. So, the last 2 classes we reviewed linear regression and logistic regression. And so, next slide. What was linear regression again? Linear regression was a way of finding a quote-unquote line of best fit. And what this, and so we would have like data points and we try to find the line of best fit. And so let's first take a look at our data set. Right now it's delays due to traffic corresponding to inches of rain. And let's say we're like, Californians. So 1 inch of rain causes like massive delays in traffic, and it goes all the way down to like no inches of rain causes a little bit of delays in traffic because that's natural traffic. And so then the task is that given these red data points, we're trying to find a way to predict how many hours of delays of traffic will we get. And so that's what this blue line represents. The blue line is our linear model's set of predictions. And what this means is that if we have 0.4 inches of rain, then the model will predict about 1.5 hours of delays due to traffic. And then so the original statement of linear regression is like finding the line of best fit, just means that linear regression is trying to find the set of predictions that give the best results, if that makes sense to everyone. Okay.
Linear regression is that so when you see new data which you've never seen before, then you can make an educated prediction.
Precisely. Oh yeah, and so this is the algebraic form of linear regression. Y equals mx plus b, because that's just the form of a line. And then assuming that we have the proper m and b, then given like a new data point, we can just plug that in and then get a new prediction, like what Nindi does that. Yeah, and so last class we went over logistic regression, which was a way of predicting probabilities this time. So again, let's take a look at our data set. Right now we have tumor length plotted here. It's from 0 inches to 1 inch, if that is a bit too faint for anyone. And on the y-axis, it's how likely the tumor is going to be malignant. So consider the data points, right? In reality, a tumor is either 100% malignant, as in it's malignant, or not malignant at all. So the probabilities of malignancy are always 100% or 0%, and that's the real life data. However, our model decided, we allowed for our model to predict 50% probability and be a little bit unsure. And then so I think the question, and so the actual formula of logistic regression was y equals sigmoid mx plus b, where sigmoid was a function that gave us this curvy shape, and mx plus b was just a line. And so what we did was we would plug, given a new data point, we would plug that into this mx plus b, and then take the output of that and then plug that into sigmoid. And I guess it's kind of hard to explain the actual sigmoid function based on, or without going into too much mathematics, but yeah.
The general idea that it washes the output to between 0 and 1, which means it's convenient for modeling probabilities.
Yeah, and so let's get a sense of how we got this. So next slide. The basic idea was that we wanted to predict, probabilities that something is malignant. But the only way we knew how to do this was with linear regression. And the problem with linear regression was that if, for example, a tumor was this big, it would give us a probability of being more than 100% malignant, which is blatantly that can never happen. So then the idea was we would take the output of linear regression and put it into this sigmoid function, which would give it a curvy shape. And so even if the linear model predicted that it's 1,000,000% probability that it's malignant, after you put it through the sigmoid function, you would only get something really, really, really close to 100%, or yeah. Okay, yeah. And then afterwards, after we got probabilities, we would pick some certain threshold. For example, right now I'm using the threshold of 0.5, and what this means is that if it's more than, if there's a probability of more than a half chance that it's malignant, then what's it called? It would just be classified as malignant, and that's how. Because right now we're tackling a regression problem of the probabilities that something is malignant or not. But after we apply the threshold rounding function, we're then tackling classification, because our outputs are then only not malignant or completely malignant. Yeah, if this makes sense. Okay. And so finally, we're going to be going over the concept of a loss function. And the idea of a loss function is that if we take a random guess at, or if we have our linear model and then take a random guess at and make a random set of predictions, right? we can see that like this set of predictions is pretty bad. And in fact, we can quantify that. I'm not going to actually go into the mathematics behind it again because that might get a bit hairy. But the idea is that this is a really bad prediction. And then we can make small increments to the slope and the bias, or the y-intercept, to make it a better prediction. I think there's a good animation on the next slide that kind of shows it. Yeah, so at first it starts off at a really, really, really bad prediction, blatantly like this line. But then the model itself knows that if you made a little bit of an adjustment to the slope, that prediction would be a little bit better, so it does that. Likewise, the model knows that if you decrease the y-intercept a little bit, the prediction would be better, and so it does that as well. And so slowly but surely, it makes little increments of adjustments that makes the predictions a little bit better, and then finally it gets to like close to the optimal solution, or it gets to the optimal solution. And so right now, this might seem chill for linear regression, but I guess it's a little bit harder to see how it applies to logistic regression. And yeah, and so I couldn't really find an animation online of showing how linear regression or logistic regression would like kind of tweak itself, so I kind of made one myself. So basically, at first it starts off with a pretty bad curve, and then so it gets, as it continues, it gets less curvy, and then next slide, and like even more less curvy until a point where it gets more curvy in like the opposite direction. And so it's hard to see because of it's hard to see right away how it's working because there's a complicated sigmoid function in the way. But basically, again, the concept remains the same. It makes small adjustments until it's reached like a pretty decent guess. And yeah, so yes, okay, so now moving on, we're going to be like doing things that can tackle much more complicated results. So this is a data set that we would not be able to predict right now. Right now we only have the tools of a single line and a curve, a sigmoid curve. But what if, like, of course, there are sometimes data sets that are maybe just a simple quadratic, and we'd want to tackle those. And so, question, how would we do it? And the answer is like you would use neural networks. And yeah. So
basically, neural networks are for modeling nonlinear functions. And so if we want to model a nonlinear function, we're not going to use the equation y equals mx plus b, because that's a linear equation. So here are examples of two. We call them activation functions because the basic idea is that they're nonlinear, and we want nonlinear functions to model nonlinearity because the composition of linear functions is always going to be linear. So here are two sample activation functions. We've seen the one on the right. It's the sigmoid function. It squashes all outputs to between 0 and 1 for probabilities, and the one on the left is called a ReLU. This basically is the equation f of x equals the maximum of 0 and x. So it just kind of takes everything that is negative and flatlines it, and then is just linear for the rest of the plot set. Are there any questions about this concept? All right, next slide. So basically the idea behind a neural network we can kind of see in our own brains. So the way our brains work is that the individual neurons send messages to all the other neurons. So it's like one neuron by itself isn't really powerful. It is the messages which send to other neurons that kind of determine the final result.
Yeah, and I guess I should mention that. So a neuron takes inputs from its neighbors and sends outputs to other neurons, but only if like the inputs surpass a certain threshold. Like that threshold is like this activation function. So, yeah.
Uh,
And I guess the power of neurons.
the power of neurons is in numbers. So the more neurons we have, the more complex of a decision we can make. This analogy is we can see it in neural networks as well. Like the more layers and the more neurons we have, the more complex our predictions can become. So a neural network itself is made up of many neurons, and these neurons are organized into different layers, and different layers perform different tasks. So here's a really simple neural network which doesn't actually do anything to make predictions. It takes inputs and then it has an output layer. So here in this diagram, the arrows represent represent weights and inputs. So we've encountered weights before when we studied linear regression, where it was like y equals wx plus b, and w and b were the respective weights. So the idea is that the weights are what we are changing in order to learn the data. And so in order to be able to make these complex decisions, neural networks have something called hidden layers. So the hidden layer's job is to take the input and to transform it into something that the output layer can use. Because sometimes the input is an image, and you want the output to be a probability of whether it's a cat or a dog. So this transformation is the job of the hidden layers. So here is a sample diagram. So another way to imagine the concept of hidden layers is that suppose you wanted something to determine whether it's a cat or a dog. Or maybe even simpler, if it's a cat or not a cat. So if something is a cat, you'd imagine you'd want smaller scale detectors. You'd want something which can detect the whisker, something which can detect the cat nose. And so these smaller tasks are what each of the hidden layers do, and they all feed into each other. The output of one hidden layer can be the input of another hidden layer, and they I guess you could say they combine all their knowledge to provide the final output or the educated guess.
So we start off with this idea of a hidden layer because a neural network was basically exists because of their hidden layers and the complex properties it does. Now I guess we'll go into the structure, and then after a little bit of talking, we'll be able to actually go through the procedure of how a neural network fires. But for now, a neural network has a neural network has an input layer, which inputs all its data. Like each neuron here would correspond to just like a piece of data. The neural network has then hidden layers. The neural network has hidden layers, which take inputs from each of the neurons of the previous layers, multiplied by a weight. Again, right now we'll go into the procedure later. Right now it's good to see, just to know it intuitively. And then finally there's an output layer, which at the end of the output layer it gives it returns an output that is your prediction. So, and by the way, you can have more than one hidden layers. Yes. Yeah. So let's take an example, and hopefully that will make this process a little bit clearer. So let's say you're a doctor or some medical person, and you're trying to predict, you're given a patient with a certain number of symptoms, like maybe they have a rating of how much they're coughing, how much of a rash they have, whether they have a headache or not, and how much of a fever they have. And let's say you're trying to predict the probability that they're going to live or the probability that they're going to die. Go back. So right now it's pretty hard to just do this with, coughing, rash, headache, and fever. That's a pretty hard task. Like if I'm coughing, that doesn't indicate that I'm going to die, but it doesn't indicate that I don't have a deadly disease either. So the way that we do this is by using a hidden layer next. So hidden layers represent intermediate aspects that are useful to us. So for example, if something, next layer, or if we knew that someone had pneumonia per se, right? then they might have a high probability of dying. For those of you who don't know, pneumonia is a condition where the lungs fill up with fluids, and then the lungs are more further susceptible to bacterial infections. Yes. And so yeah, pneumonia is a pretty high indicator of death, kind of. But for the example, let's say it is. On the other hand, if the coughing and the headache was just from allergies, that's probably not that fatal. And so that would be a low indicator of the probability of death. And right now I'm using the terms like strong indicator and negative indicator. So like pneumonia is a strong indicator of death, but pneumonia is a negative indicator of life, because if you have pneumonia, you might not live. But what this really means is that, so that's what it really means is that these connections have a positive. The green connections have a positive weight, and the red connections have a negative weight. We'll go over more of this in the procedure again, so I don't want to intimidate you guys too much with all the talking of weights and stuff. But yeah, for now, just know that this strong indicator can be converted into something that's like more mathematically rigorous, I guess. So yeah, so that's the concept. And so now we want to know, well, so if we know that someone has pneumonia, then we know that they might die. But then how do we know if someone has pneumonia? That is the question. And so the answer is that we can use our input layers to actually give us like a sense of what hidden layers are active. For example, coughing and fever are strong indicators of pneumonia, and while having a rash isn't a strong indicator of pneumonia, because a rash is probably caused by something else, not pneumonia. So, wait 1 second. So, yeah, so then basically, based on our input layers, we can kind of see which hidden layers are working, and based on like which hidden layers are working, we can kind of see if someone's gonna die or live.
So like intuitively as you're following along, you think like, if I were the person making these decisions, how would I diagnose pneumonia and like see if the neural network demonstration which all of us doing kind of matches with your own that's what makes sense.
Yeah, and like I guess next slide, or it's fine. So likewise, we can kind of figure out how much like of an allergies value we want to give a patient. If they're next slide, if they're coughing or if they have like a headache, those are like strong indicators of having allergies, and then they probably will live and like not die because allergies aren't that fatal. However, if they have a fever, that might not be an indicator of allergies. Yeah, and so I guess the overall general idea that I want you to come away with is that hidden layers are a way of breaking up like a complicated task of maybe predicting, and in this example, it's predicting life or death, and then it's a way of breaking up a complicated task into simpler tasks whose results we can then use to predict the complicated task. And to do this, I think we're going to be going to somewhere called Playground, TensorFlow.org. Playboard. Huh.
Basically, on this website, you can interact with the neural network, match the number of neurons, the number of hidden layers, and you can do it all without writing any code. So it's good for developing intuition.
Yeah. Do we want to give a demonstration as well? Yeah.
Is anyone unable to access the website?
We have to like drag it across, I think. No. Yeah, let's try using this data. I think that data demonstrates the point the best. And then go to like 3 hidden layers. Yeah, and
It's playground.tensorflow.org.
okay, and so I'll give a brief explanation of what's happening. So right now you have a set of data points, and you're trying to classify where, or you're trying to figure out which, yeah, if you're trying to classify, if given a new data set, or if given a new data point, would it be blue or orange? And so basically, here you have a neural network. These are input neurons. These are hidden layers. Or wait, what?
Like when you hover over them, your mouse can show.
Yeah, and so try running it.
So the play button causes you to review that to train. So this on the right is our loss. So you can see as it trains, as it gets better and better, the loss keeps decreasing. And you can see how it's trying to form that checkerboard.
Pattern, yeah.
And how after a while the training loss stops decreasing so much and it starts, and it starts becoming really, really confident in its guesses.
And so, what's it called? Epoch is like kind of a measure of how much it's training. It's a run through of the whole data set. You can increase hidden layers. You can add more neurons to hidden layers. You can switch data sets. So let's give them a moment to play. So yeah, you guys can like try playing with the model a bit and like, yeah, have fun.
Well, something interesting to do is like try editing the weights after you train them and
Artificially building your own one.
Yeah, and try like see if you can throw it off or get it consistent.
Yeah.
The hardest data set I think is the spiral.
Yeah, definitely.
So the challenge for that.
Yeah.
You can also adjust the number of neurons. Remember what we said earlier that having more neurons makes it able to do more complex things. Add inputs. You can add hidden layers too. Have fun.
So I think.
This one's kind of like linear regression. Like you just have to, it's kind of like studying a line. Oh, it's more like linear regression. about around a minute more to benefits, but feel free to tinker with it during implementation. Alright, I think we're gonna go now. Yeah, sure.
Okay, and so I guess one thing that you guys should have all noticed if you guys were playing with the thing is that each neuron's hidden layers like start off more simple and then go to more and more complex ideas. So like, for example, this neuron is a simple idea of like a single like blues over here, oranges over here. But then if we combine this neuron with like the rest of its neurons and like this neuron, or maybe this one. So if using the other neurons as input, this neuron can construct this idea that over here I'm not sure, but over here is probably orange, over here is blue, and over here is blue. And likewise, the layers of complexity just get higher and higher and higher until you have your final output, which is just what's it called? Or so now we're just going to be going over like the actual procedure of how a neural network works.
Yeah, we're gonna look into how a neural network calculates the answer. This is just like the inputs are just numbers, and the outputs will also be numbers here. So suppose like the inputs are like what a doctor has inputted, like the probability of him having a big cough is like 5, or like suppose like these are all out of 10 or something. And then these are the weights that the neural network starts out with. And so what we're going to do is we're just going to pass these inputs with certain weights through this network and see the answer that we come up with. So in order to calculate this, what we do is we take the input times the weight, and we add all of them together. So we take 5 times 8, 1 times -4, -2 times, I believe that's 2, and 9 times 5. And we add them here.
What would we get?
Mental math. Quick maths. Oh, you do. We can go on.
Okay, so yes, 77. And then
So after we have our answer, this is where the activation functions, which we mentioned earlier, come in. After we have our answer, we have to pass it through an activation function. Can anyone tell me why? We covered this earlier. Why do we have to pass our answer through an activation function? We have to pass something through an activation function, because if we don't, then the function we're predicting is just linear, and we don't want that. So, yeah?
activation functions are what makes neural networks like non-linear. They're like the essence.
So we choose an activation function. Let's just call it A to be general. And then we can do the same for all the other neurons as well. Yeah. So here we used the ReLU, which is the max of 0 and x. So A of 77 would just be 77. And so suppose that we've gone through all of the other neurons in our hidden layer and have done the same for them. So if we didn't use the activation function, then what we're doing is we're multiplying things and adding them. So then that would still be a linear function, but the activation functions are nonlinear functions. So having them means that our neural network can now model nonlinear relationships. So yeah, so suppose we've done all that, then we can calculate the probabilities here. By doing this much the same procedure, we take the values and we multiply them by the weights. And so we get a number for our probability, but remember that we have to squish all the numbers between 0 and 1, otherwise they wouldn't make sense as probabilities. And so we pass it through an activation function. This time we could use a sigmoid activation function because it squashes, because it's the one which squishes everything, and we like it for classification. And then we get, yeah, and then we get a probability.
I guess we can see ReLU in action over here for A times A of negative 53 and A of negative 72 because they both turn into 0. So yeah, one of the... So now, I think everyone should be wondering one thing, like, how do we get these hidden layers, and like, how do we get the idea that maybe one hidden layer represents pneumonia and another hidden layer represents allergies? Well, so let's consider what the machine knows about pneumonia and allergies. The machine, The machine doesn't actually know anything about that. It doesn't know that this neuron represents pneumonia. All it notices is that when you're coughing and when you have a fever, and you don't have a rash, then you might die. Likewise, if you're coughing and have a headache but no fever, then you probably will live because, and upon further examination by a human, we know that the neural network is grappling with the idea of like allergies, but the neural network doesn't actually know this itself. And I guess over here I can explain what I meant by by strong indicator earlier. Anything with green is a strong indicator, meaning that its weight is like high. And for example, if you're coughing and you have a green weight with a high positive number, then you're likely to have allergies. However, if you have a fever with a high number, then the negative weight turns that into a negative number, and then it's added to the total sum. And so that means you have a lower value for the allergies, I guess. Yeah. And so one last detail is, actually, first, do we have any questions? Yes. Yes. Okay, so go back. So that thing was a question that evaded a lot of people for, I think, 100 years or 50 years? 50 years or so. The actual process is called backpropagation. So neural networks were developed in the 1950s, I think, but no one knew how to train them, so they were largely forgotten. And then one guy went back and discovered a method called backpropagation and figured out how to train these. And everything was like revolutionized. Yep. Precisely. So like if it knows like how much maybe it overpredicted for like probability that it's gonna die, so then it might penalize all these weights and like turn them down a bit, so that maybe the value of pneumonia is maybe less, and yeah.
So if you guys know the gradient method for the whole thing, minimizing total error, it's kind of the same thing, except like we're adjusting the weights in all the layers in order to minimize the final error again.
Yeah. Okay, and are there any more questions? Because neural networks are complicated.
So you're saying that the weights are calculated using backpropagation?
Yeah, and I guess precisely they're not calculated, but like iteratively stumbled upon, if that makes more sense.
So we begin with
So you experiment with several weights until you are able to arrive at a particular weight that makes
Kind of, yeah. Okay, so, oh, back. All right, so,
back propagation because you are looking at death resulting from pneumonia and then pneumonia resulting from these times.
yeah,
So you're going backwards.
yeah. Okay, and so then, so this is like the last tidbit. So yeah, stick with me. So one thing that we might notice is that probability of living and probability of death actually is very correlated. So if you have, you know, if you have like probability of life going to be like 0.7% or 70%, then the chances that you're going to die should be 30%. That makes, yeah, that's how it should be happening. So the way that we tackle this problem is that we don't actually, the activation function for the last layer isn't sigmoid. It's something called softmax, which is sigmoid and then a weighted average to make sure that they add up to 1. This sounds complicated, so let's break it down. So what happens is that, let's say your neurons have, you've already done your neural network calculations, and your final neurons have values of 0.9 and -2. So then we first put them through the sigmoid independently, and then we get different probabilities. Since it's sigmoid, the probabilities are going to be from 0 to 1 and 0 to 1. And then we take a weighted average, and then we can get new probabilities. And what this weighted average does is that the results will then add up to 1. And that makes it a lot more accurate. Or, yeah, kind of makes more sense that way. And like this whole process of sigmoid and then weighted averages is called softmax. And I guess we mentioned this because if you're gonna, or it's important to know if you're gonna build a neural network from scratch. I don't think we are because we're using sklearn, and sklearn is incredibly convenient. But yeah, that's it for now, I guess.
In general, what can we use neural networks to do? You can process lots of data, and all the examples we have really small inputs, but real neural networks are massive. They learn the properties of data and generalize those properties they've never seen before. And this could be really exciting. Like I think today we're going to work with a breast cancer data set, which is it's in scikit-learn already, which is like pretty like exciting and real world stuff. I wanted to give you guys enough time to have an hour to implement. It's 4:50 right now.
4:50. Okay, so 10-minute break.
Yeah, about a 10-minute break.
Okay, and I think we have food in the back table. Oh, we can skip this part. Overfitting. Oh.
Yeah, so since we're taking a break, just a short note that when you make neural networks, often the first error we're going to run into is called overfitting. Overfitting looks something like this. So this is a nonlinear function which fits way too close to the model. I think we briefly touched upon this in the first stage. So basically the reason that overfitting is really bad is because it doesn't generalize. So when you're building a neural network and training it from scratch, you'll want to check that. So you'll probably want to check that that doesn't happen.
So I think we'll send out, since we didn't get to actually explain overfitting into that much depth, we'll send out another video that will explain overfitting like better. So yeah, another break now.
These slides are on your website.
Yeah, we'll put them on. So who wants to talk?
All right. You could talk.
So
So we sent everyone an email with some and then we're going to walk through how we came up with this, how we made this code, and then we're going to send everyone a regression neural network, a regression data
Oh, that's
set,
fine.
and have a challenge of who the two largest are.
So yeah, yeah. If at any time you have any questions at all, please ask us. Also, exists like the sklearn documentation if you want to look into that as well. Okay. So everyone should go into Kaggle and like create a new kernel, and oh yeah, new notebook. Yes. And so.
And so I believe I separated them out, like according to the percentages that
Yeah. So, is everyone on like Kaggle and ready to begin? Or hands up if you're ready, I'd say. Okay.
So in the beginning, we're just going to kind of try and get a feel for the data.
What?
So
Data.
this
Can you
is,
make it bigger?
let me see.
Mm-hmm.
Zoom in?
Oh yeah. Zoom works.
Is that better?
Yeah.
Wonderful.
Actually, didn't get the email.
Oh, you can get the email. Oh, okay. I will send it all on the screen. Oh, yeah. Awesome.
Oh wait, does he want the email? Or do you want the email?
Yeah. I think you can send it to everybody.
Oh wait, are you on the mailing list?
Yeah.
Ah, I see.
Does everyone have the email?
Yeah.
Okay, cool.
Okay, so now raise your hand if you're ready for us to move on. Okay. Okay. All right. So I guess we'll start then.
So where do you go? You go to
It's Kaggle.com. So here you can write machine learning code without having to implement download a bunch of stuff. Oliver, do you want to help me get that?
Sure. Use the headset.
Oh, thank you. Right. So now we're going to walk through how people build and design a simple neural network. So scikit-learn has a class called the MLP classifier, so basically this is a neural network which does classification. The dataset we're going to use is called load breast cancer. So we define a variable to call the dataset. And yeah, a bit bigger. The screen, sure. Is that more visible? Cool. And then we can do something called cancer.keys to show us the different features which this data set has. So these are the kind of keys. So the data set's organized like a dictionary, and here are the kind of keys that we have. And so our X our input's going to be our data, and the y values are going to be our target. Like that's kind of what we mean. So in order to kind of see what the data looks like, we could try running. Try running these two lines. So this is this is the y values, I believe, and up here are the x values. So we have to do more research into uncover exactly what the data set is in order to see exactly what these represent. But intuitively we can see that this is a binary classification problem because there are only zeros and ones in the y data set. So I'd advise you guys to kind of poke more into the data set and see exactly what everything means. You can probably look it up on the Escalator implementation. Okay, so in order to divide the data into training data and testing data, we can import something from scikit-learn called train test split. This is kind of like 80% of the data goes towards training your model so that your model can become better, and 20% of it goes towards testing. By the way, if you want to follow along with this tutorial, go ahead. If you want to explore the data on your own, feel free to. Now we're going to do something called scaling or normalization to our data. So basically, we use scaling in order to make our neural network converge to good weights faster. So the intuition behind this is like, suppose we have 5 features, and one of the features has values ranging from these really big numbers, or around these really big numbers, and another one of the features is 1 to 5. Then the neural network wouldn't know that they're so far apart, so it would take a long time to kind of converge to a good weight. But if we squash all of them, so that, say, all of them range from 1 to 5, then the neural network will kind of converge to its right weight faster. So in order to do that, we implement something called standard scalar. So I think this makes it such that the mean value is 1 and the standard deviation is around 0. And we only do this to the training data because the test data could be wild and crazy for all we know. So now we're going to implement the neural network itself. So this neural network is going to have we can decide the number of hidden layers, the number of neurons on each layer that we want it to have. So hidden layer sizes. I think in the code I wrote 20, 20, 20. We could have 50, 50 if we wanted. It would probably do better the more neurons we add. And then, much like the linear models we experimented with earlier, then we fit our training data to the classifier. And the idea of fitting is that we tell the classifier that these are the data this is the data we want to learn. Then we run it. get an output that looks something like that. Here you can see the activation function it uses. It uses the ReLU activation function, which is max 0 and x. You can also play with this yourself and try changing the activation function when you describe it. So like you could be like activation. Oh, sorry, let me just think. You could try different activation functions yourself. See what you come up with.
And so right now we're using a library called sklearn, yeah. And so sklearn doesn't call neural networks. It calls them MLPs, or multi-layer perceptrons. But MLPs are just neural networks, I think. And so, yeah, right now we have an MLP 50, 50, 50, which means it has 3 hidden layers and it has 50 neurons each hidden layer. And then sklearn is really nice, as in it will automatically provide the input neurons and output neurons based on your data. But yeah, so sklearn is really, really, really convenient. And yeah.
So we have our model now. So let's see how good or bad we're doing. In order to do this, we can try predicting on a test data. So note that the test data is the one which we can't touch when we're training from. The test data is the one that keeps on it. So if our model does really well on the training data, but it kind of fails on the test data, then that means that it doesn't generalize new data very well. That means it's kind of useless and it's overfitting.
Alright, please raise your hand if you're up to speed right now in the code.
If you have a question, then feel free to push it here or even right now. So this is a kind of metric where you can see like how good you're doing. So classification report kind of takes the difference between like what your model predicted and what the actual values are. So if we run this, metrics, sorry. S. Yeah. So there are many different ways to. We could kind of go. Yeah.
I think hopefully helps. So we might go into precision and recall later on in the future, like S4 and everything. And
Basically, the higher these values are, the better you're doing.
Yeah, basically.
Yeah. Awesome.
So
I think now we're going to send out everyone a bit more code. This time we're going to ask people to implement an MLP regressor. So that solves their regression problem instead of a classification problem. So you're going to follow similar steps and develop it in the same way. You guys have the code. If you have any questions, let us know. I'll send an email with something. Yeah, sure. The first one. This is the first one. Yeah, you just did it for the rest of the day.
the next data set, or the next code that you might be implementing, is kind of purposefully left a little bit vague. And I guess that's to like give you more freedom in what you try. And yeah. So good luck. That's coming around to Nandita. And like this one, you probably will have a lot of you might have a lot of problems or trouble doing. It's challenging. So don't be afraid to ask questions.
Hopefully
Questions are
not
like,
that much data cleaning though, that's kind of nasty.
yeah.
I should have set up the email to everyone, if you didn't get the email, send that email. Did you get the email? Yeah.